Hey guys, welcome back to our next lesson. Today we're going to be talking about, I'll say, deeper differences. And that just means we're extending our understanding and our use of difference tables to more than just linear functions. So our mindset message today is that mistakes are important. Mistakes are a necessary process to learning things. I've heard this saying once that it's not really a mistake unless you don't learn from it. And that's like a really good lesson, I think. Our learning goals for today are, first of all, to understand that constant second differences, which we'll talk about what that means, match a quadratic function, and also to actually find a closed form rule for a quadratic function. Basically, your prior knowledge today is to know how to make a difference table, as well as just remembering what a quadratic function is, and I took the liberty of writing it here. A quadratic function will always be in this form. It's a second degree polynomial. Remember, that means the highest exponent is 2. So it's always going to look like ax squared plus bx plus c. So a, b, and c are just any numbers. So it could be 5x squared plus 8x minus 2 or whatever. With that said, let's go ahead and dive into our first kind of initial question just to think about for you. What could be a closed form rule for this table? This question is kind of our goal to answer by the end of the lesson today. We're going to have to do some stuff to be able to get to the point that we can actually find a closed form rule. But what might be your natural inclination based on what we've been learning lately if I'm given this table to look for patterns in it? That would be to use a difference table, right? So why don't we actually start by making the difference table for this, which I've of course already set up. So to get from 1 to 2, I add 1, right? 1 plus 1 is 2. 2 plus what is 13? That would be 11, right? You can also just subtract this minus this, of course. And then from 13 to 34, that's going to be 21, I believe. And 34 to 65 is going to be 31. Now, right now, this does not have constant differences, right? So we know that this function can't be linear. But if you look carefully at these differences, it's pretty easy to tell that there's a pattern going on there, right? So this is where we're going to bring up what we talked about with second differences. Second differences are what they sound like pretty much. You would just take this to another level, and it's the difference of the difference. Now, normally the way we write this is with the 2 up there. Be careful because that doesn't technically mean squared. So it doesn't mean I'm taking this number and squaring it. It just means I'm taking the difference of the difference. So that's something to make note of for yourself in case you think you might get that confused later with exponents. And the cool thing to see here is, oh, wait a minute. From 1 to 11 is 10, and then from 11 to 21 is 10, and same with from here to here is 10. So it turns out that the second differences are constant, even though the first ones aren't. And we're going to prove right now, basically, that this situation actually will always match a quadratic function. So let's take a look at a proof of that over here now. Okay, so I've set this next thing up for us. Make a difference table for the quadratic function f of x equals ax squared plus bx plus c. So you'll notice I did not put specific numbers in there for a, b, and c. So instead of asking about what's the specific difference table for like this particular quadratic, what we're kind of saying is let's make a general difference table that represents all quadratics, and it'll help us figure out formulas for pieces of this that are important. And in the end, we'll actually be able to prove the statement we made that second differences always match a quadratic function, but it'll also give us a tool to use to be able to actually figure out those closed form rules. So let's dive in here. When x is 0, remember, we're just plugging 0 in for x here. So 0 for that and 0 for that. And if you actually simplify that, you can see that a times 0 and b times 0 are just gone. All we're left with actually is c. So 0 gives me an output of c. 1, however, does something a little different, right? Because when you put 1 for x, a times 1 squared is just a, and then 1 here. So this becomes a plus b plus c. And similar thing here for 2. If x is 2, 2 squared is 4. So I have 4a. And then when x is 2 here, it's just 2b, and then just plain old c. Why don't you pause right now and finish filling this column out for 3 and 4, and then we'll get to looking at the differences together. All right, let's check this. What you should have gotten here is 9a plus 3b plus c. It makes sense because it's always this squared and then itself and then just c, right? So that makes this 16a plus 4b plus c. All right? Now what we can do is say, okay, this looks kind of ugly and complicated, but it's doable if you just are careful. Let's make the first differences here. If I'm at C, what did I add to get to this, right? What do I need to add to get here? Well, there's an A and a B, right? So here it's going to be A plus B. So C plus that gives me that, right? And then we can do the same thing. From here to here, notice that along here C is just staying the same. So I'm never going to be doing any adding of more C's here. But I am adding some A's and B's. How many A's did I add? 3. And how many B's? Just 1. So it's 3A plus B. And then from here to here, I added 5 A's and also just 1 more B. Let's do the same thing again where you pause and just fill the last one out there. There's just 1 more. Okay, let's look at this. This is going to be 7A and then still just 1 more B added. Now it's maybe more obvious that there's a pattern happening here. And notice that the B's are now constant. So the C's stayed constant there, the B's are now constant here, and it's just only the A's. So the only thing we're going to have in the second difference column is just A's. So what did I add to this to get this? 2 A's, didn't I? And then here I added 2 A's, and here I also added 2 A's. Interesting. What do you notice? Exactly what we made the claim for is that once you get to the second differences, not only is it constant, but it also actually has a specific relationship between that A value that we're going to be looking for. Okay? And this is going to help me out with finding a formula for our first example, which we're going to do here in a moment. All right? So, conclusions from this. One thing is important to note. This guy right here and this guy right here. This will help me find A, and this will help me find C, okay? And I'll write this. C occurs when x equals 0, which I guess we already noticed, right? So in your table, whatever that number is when x is 0 is always going to be your C value if you're trying to find the closed form rule. So, and then whatever this number is, the cool thing is you can just take half of it to figure out what goes there. And the only thing left is to figure out what the B is. Let's actually do a practical example. I'm going to erase this part and we're going to finish this off together. So make sure you have this guy in your notes right now. Okay, now we can break down this barrier that we had up because we didn't know what to do before. Now that we know what to do, I want to remind you guys here that whatever this number is always 2A. So we can say 2A equals 10, and that means A must be half of that, right? And then right here is always going to be the C value, so we can say C equals 1. This is good, because what I can do then is say, well, okay, first of all, first thing to note is that the second differences are constant, so it must be a quadratic. That's always something to look out for. If you see the first differences are constant, oh, we know that's linear, so I'll make a linear formula. But when the second differences are constant, you know it must be quadratic, okay? And so because we know it must be quadratic, we know that f of x equals ax squared plus bx plus c must be the formula we use. But since we realized that, or we figured out that our specific a value here is 5, and our specific c value here is 1, this is really nice, because we're like almost done. The only thing missing here is I still haven't figured out that b value. The thing about b that's a little, I don't know, annoying, I guess you could say, is that it's not directly findable by just one single number in this table. But I think the easiest way to figure it out is just choose any of the coordinate pairs, except this first one, because when you plug x as 0, it makes all the x's go away. But if you want to choose any of these coordinate pairs, you could use them and plug them in for x and f of x, like as input and output, and that'll help you solve for b, and then we'll get our final formula. So let's just say I chose to use 2 and 13. So what we're saying is the output is 13 when the input is, and I'll try to keep all my color coding. Here. When the input is, what I say, 2, and then we still don't know b, but again, we're using 2 as our x value. Okay? So you should be able to see where everything came from, is that this 2 and 13 here is what I used as my input and output, and this becomes an equation I can just simplify and then solve for b. So finishing this off here, I'll just use this blue color to finish off. 2 squared is 4, times 5 is 20. B times 2, let's just leave that as 2b plus 1 equals 13. And let's see here. I want to subtract the 20 and the 1. So if I subtract 1, that's 12. And if I subtract 20, what I get is negative 8 over here equals 2b. So I just subtracted those numbers over there. And then my last step would be to divide by 2. And guess what? I get b equals negative 4. So I've actually finally solved this problem of finding a closed form rule. My b is negative 4, so instead of plus, I'm going to write minus 4. And here's my final answer for number 1. F of x is 5x squared minus 4x plus 1. That's a really, really cool way to figure out a formula for a quadratic. The other methods that are used often in courses like this are actually significantly longer in their steps. And this is just a really cool, nice way. And this actually, just so you know, what we're doing here is basically like the ideas of calculus, just so you know. So this is an important way to understand this, to lead towards the ideas in calculus later on. Let's give you a little bit of practice with a couple more problems, and then that'll be it. Okay, so to wrap up today, here's the 2 practice problems for you. Confirm that a quadratic function fits each table. Remember, that just means confirm that the second differences are constant. And then confirm the given closed form rule fits. Okay, so I actually gave you the closed form rule, but do the process we talked about in the last example to finish that off. Okay, so go ahead and pause right now and make the difference table, confirm that second differences are constant, then we'll look at that together, and then we'll have you pause again and do the rest to confirm the formula. Okay, let's check your difference table. From negative 4 up to 1, I went up by 5, right? You could also just think 1 minus negative 4 becomes 1 plus 4, which is 5, okay? And from here to here is 9, and then 13, and then from there is 17, and that makes my constant difference between these differences, right? The difference of the difference is 4. So check, constant differences and second differences must fit a quadratic. This guy here, this is actually decreasing each time, which is okay. From 6 to 4, I went down by 2, right? So this is going to be negative 2, and from 4 to negative 4 is negative 8, and then from negative 4 to negative 18 is negative 14, and then from here to here is negative 20, and then it turns out each of these is going down by 6 each time. So again, we have a constant second difference for that, and it also must be quadratic. So again, now go ahead and pause and finish doing the process we talked about to confirm the values of A and B and C. All right, checking this. Remember from the table, whatever this constant second difference is always equal to 2a. So if 2a equals 4, then a equals 2. Check. Remember that whenever x is 0, that output is always c. Check. And we can confirm the same thing here to get negative 3 and to see that our c value is 6. Now it's just a matter of calculating the b values. I like the idea of 1, 1. That's just nice, easy numbers to work with. But again, you could have chosen any of these other input-output values for your output and input. But if x is 1, this becomes 2 times 1 squared, so it just becomes 2 plus 1b, so 2 plus b minus 4 equals, and remember that gives an output of 1. And so if I add 4 here, that makes 5, and if I subtract 2, I get that b equals 3. And that is exactly the b value that we had stated before. And then, same idea from this, we could just use 1, 4. So our output is 4 whenever our input is 1. And again, a nice input of 1 is nice, because that just makes it equal to the coefficient there. So negative 3 plus b plus 6. And if I add 3 and get 7, and I subtract 6, I get b equals 1. And so it becomes plus 1x plus 6. And that's what we had before. We just wrote x, of course, but that's equivalent. So, there we go. Happy math, and we'll see you in our next lesson.